Welcome to the Padhshala lecture series in computer science. We are looking at the computer architecture course. This module discusses about multiple issue processors. So the learning objectives are to discuss the need for multiple issue processors and to discuss about statically and dynamically scheduled superscalar processors and to point out the complexities involved in these processors and the design issues. So, if you look at the need for multiple issue processors, in all the modules that we have discussed so far, we have looked at different techniques for exploiting instruction level parallelism, both at the hardware level as well as the software level. And with so much of exploitation of ILP happening, we are still issuing only one instruction every clock cycle, and what we expect is one instruction to finish every clock cycle. So, the maximum that we can expect is a CPI value of 1. So, in spite of whatever hardware and software techniques that we exploit. So, if you want to reduce your CPI value to less than 1, then obviously we will have to look at issuing multiple instructions. Say for example, if you are issuing 2 instructions every clock cycle, then you also expect 2 instructions to finish. So, your CPI will reduce from 1 to, ideally it should reduce from 1 to 0.5. So, we will have to look at multiple issue processors if we have to look at reducing the CPI below 1. So, now if you have to look at multiple issue processors, the simple technique is you will have to extend the simple pipeline, because if you are issuing multiple instructions every clock cycle, then every stage of your pipeline will have to be capable of handling this multiple issue. So, you will have to have multiple functional units, for example, in the execution stage, or you will have to increase the depth of the pipeline so that the execution units are capable of handling multiple instructions. And this is obviously the depth of the pipeline, increase in the depth of the pipeline is required because of the increase in clock speed. Now, so increasing the width of the pipeline for multiple issue processors means that several instructions will have to be fetched and decoded in the front end of the pipeline. So, obviously that unit will have to be enhanced so that you fetch multiple instructions every clock cycle, you decode multiple instructions every clock cycle, and that is how you can issue multiple instructions to the pipeline to the back end. And similarly, if you have multiple execution units there, then the execution units, either multiple execution units or pipelined execution units, they will be able to handle the execution of multiple instructions. So, if M is the maximum number of instructions that can be issued in one clock cycle, then we normally say the processor is M issue wide. So, if you have 4 instructions issued every clock cycle, then the processor is called a 4 issue processor. So, that is what is called a multiple issue processor. Instead of issuing a single instruction every clock cycle, we issue multiple instructions every clock cycle. Now, what are the different types of multiple issue processors? Multiple issue processor basically come in 2 flavors. One is a superscalar processor, where a superscalar processor may look at in order execution, which is a static scheduled processor, or it can use an out of order execution, which is called a dynamically scheduled processor. So, that is one form of multiple issue processor, where it can either be statically scheduled superscalar, or it can be a dynamically scheduled superscalar. We will discuss details about this as we proceed. The second flavor of multiple issue processors is a VLIW processor, where VLIW stands for very long instruction word. So, what we try to do is the compiler tries to form a packet of instructions by combining a number of instructions which are independent of each other and forms a packet, and this packet is issued to the processor, where the compiler takes the onus of finding out all the independent instructions and grouping them into packets. So, we will discuss more about the VLIW processors in our next module. So, this module we will concentrate on the superscalar type of multiple issue processors, both statically scheduled and dynamically scheduled processors. So, if you look at the superscalar processors basically decide on the fly how many instructions can be issued. So, if instructions are issued to the backend in order, we have in order processing. So, in-order processors with statically scheduled are statically scheduled and the scheduling is done at compile time. So, the two types of superscalar processors are in-order processors and out-of-order executing processors. In-order processors are statically scheduled, that is the scheduling is done at compile time. So, a statically scheduled superscalar must check for any dependencies that exist between the instructions in the same issue packet. They should also check for any dependencies between these instructions and instructions that are already available in the pipeline. For this, it requires significant compiler assistance in order to achieve good performance, as the compiler does most of the job of finding and scheduling instructions for parallel execution. So, in contrast, compared to your statically scheduled superscalars, a dynamically scheduled superscalar requires less compiler assistance, but the increase in hardware costs is very significant. If instructions can be issued to the backend in any order, you do not look at an in-order execution, you look at an out-of-order execution, we have out-of-order processors. Out-of-order processors or dynamically scheduled superscalars are the same as we discussed with respect to our Tomasolo's dynamic scheduler. Only thing is we looked at a single issue Tomasolo processor earlier with and without speculation. So, with multiple issue we are still looking at dynamic schedule processors, but you have multiple instructions issued every clock cycle, and these instructions will go out of order once the issue is over. So, out of order processors are basically dynamically scheduled processors by the where the dynamic scheduling is done by the hardware. So, alternative to these superscalar processors is to rely on the compiler technology and to minimize the potential hazard stall. So, actually the format of the instructions in a potential issue packet. So, you have a number of instructions put together in the form of a issue packet, and the hardware need not check explicitly for any dependencies, because the compiler ensures that dependencies within the issue packet cannot be present, and at least it will indicate when a dependence may occur. So, that way the compiler takes the burden of identifying dependencies and indicating dependencies, and the hardware does not have the complexity of doing this. So, this architectural approach was termed as very long instruction word, which was used in the Itanium processor, and compiler technology offers potential advantage of simpler hardware while still exhibiting good performance through extensive compiler technology. We will look at VLIW processors in the next module. So, we will try to get more details about statically scheduled processors. So, statically scheduled processors, you have issue packets that are given. So, basically let us say we issue about 0 to 8 instructions, that is if you are not able to identify any instruction in that packet, then it becomes 0, but if you are able to identify a few instructions which can go together, which can be issued in a single clock cycle, then it becomes a multiple issue processor. Now, all hazards are checked in hardware. Even for a statically scheduled processor, the hazard checking is done in hardware when the instructions are issued. So, when the instructions are issued, the hardware checks whether there is a dependency between these instructions, and depending on the dependency among these instructions are dynamically issued. But it is an in-order execution that happens. So, among instructions in the issue packet, any dependencies are checked, and also dependencies between the instructions in the packet and the instructions already available in the execution in your execution pipeline is checked. So, if one instruction in the packet cannot be issued, only the preceding instructions can be issued, subsequent instructions cannot be issued, because we are strictly looking at an in-order issue. So, hazard checks have a normally take a long time, and so the issue stage is split into two, and it is basically pipeline, so that you are able to handle multiple instructions. Say, so for example, if you have to look at a two stage pipeline, the hazards among instructions in the same packet can be checked in the first stage, and the hazards among instructions in this packet and the ones already available in the pipeline can be checked in the second stage. So, if you look at a statically scheduled superscalar MIPS, the MIPS architecture which we have been discussing throughout. Let us assume that it is a 2 issue superscalar. So, we assume the 2 instructions can be issued every clock cycle, and let us assume that one instruction is a floating point operation, the other one can be a load instruction, a store instruction, or a branch, or an integer operation. This combination basically reduces the risk of hazards between the instructions, because we normally look at separate floating point registers and we look at separate integer registers. So, if you have a combination of a floating point instruction and a integer instruction, the overlap or the hazard between the dependence between these instructions becomes minimal. So, that is why we normally look at a combination of a floating point operation and an integer operation. So, you fetch 2 instructions, check for hazards among these 2 instructions and issue them. If one instruction is a load, store or a move, we might have a data hazard and maybe a structural hazard for a floating point register file port, because both of them will try to access the same register port. So, this is an example of a statically scheduled superscalar MIPS. So, as you can see, every clock cycle you have 2 instructions that are being fetched and issued. So, every clock cycle you have 2 instructions being fetched, you have 2 instructions being issued. So, the same timing diagram that we discussed with single issue processors holds good here also. Only thing is we are trying to look at issuing 2 instructions every clock cycle. So, the first clock cycle you have 2 instructions, one floating point and one integer instruction being fetched. The next clock cycle both of them enter the decode stage. The next clock cycle they get into the execution stage. The next clock cycle they get into the memory access stage and then the write back stage. So, the problems that might arise here are, you may have, obviously you may have to have additional hardware in the pipeline, because you are trying to fetch multiple instructions, you are trying to decode multiple instructions and issue multiple instructions, and you are also looking at executing multiple instructions. So, you need to have additional hardware in the pipeline. Now, out of order completion among these instructions, though these 2 instructions have been issued together, it is quite possible that the second instruction may finish out of order. It may finish before the first instruction. That will obviously lead to imprecise interrupts. So, that will have to be handled, and hazard penalties may be longer here. So, the next case of superscalar processors is a dynamically scheduled superscalar MIPS. So, we are looking at a dynamically scheduled superscalar MIPS. So, as I already pointed out, we are just extending the Tomasulo's approach to handle multiple issues. So, we have already seen a single issue dynamically scheduled processor which looks at a Tomasulo's dynamic scheduling approach. We are just extending that in order to handle multiple instructions every clock cycle. So, this hardware, the dynamically scheduled superscalar, must issue instructions to the reservation stations in order, because you know during the issue stage you check for the availability of a reservation station and then you are going to issue these instructions. So, the issue of the instructions to the reservation stations will have to be done in order. So, the issue stage can either be pipelined, where you have one half of the clock cycle being used for handling one instruction and the next half of the pipeline clock cycle being used for handling the second instruction, or you can try to look at replicating the hardware, so that the issue stage itself is replicated, so that 2 instructions can be issued. The issue process happens simultaneously for both these instructions, and the issue logic may become a bottleneck because you have to issue multiple instructions and it can either be pipelined or replicated. This issue logic, as you increase the number of instructions that can be issued, it will obviously become a bottleneck. Now, you also have to limit the number of instructions of a given class that can be issued in a bundle. As already pointed out for the statically scheduled superscalars itself, when you look at one floating point instruction and one integer instruction, the dependencies may be minimal. Suppose if you try to put 2 floating point instructions together, then there might be too much of dependence between these instructions. So, that is a design issue, whether you are going to look at what type of instructions can be combined together and issued together. So, we basically have to examine all the dependencies among instructions in the bundle. If there is any dependence existing among the instructions in the bundle, in a dynamically scheduled superscalar, those dependencies can obviously be encoded in the reservation station. Say for example, if I have a load instruction and following that I have an add instruction coming in the same bundle, same bundle in the sense they are coming in the same issue slot, then when the load is issued, the load is given a reservation station, and when the subsequent add is, which is dependent on the load, is issued, you know that the reservation station registers the fact that the operand has to come from the load instruction. So that way you are able to encode the dependence in the reservation station. That is how it is done in your dynamically scheduled superscalar. So now let us look at an example as before. So you have a load instruction, you are adding some value to it, probably you are incrementing here as indicated here, and then the incremented value is just put into the same memory location by means of a store instruction. The loop maintenance code or repeating the loop is done by means of incrementing your register value, the pointer information, and just checking on the terminating condition by using a branch instruction. This is the normal loop that we look at. So now how this can be executed in a dynamically scheduled superscalar, where we are trying to issue 2 instructions every clock cycle without support for speculation, is shown in this table. So the first clock cycle you have the load instruction being issued, and along with that you also have the increment instruction or DAD-IU instruction being issued. So both of them are issued in the first clock cycle. The execution of the load instruction happens in 2 and 3, and the write result, where the result is written onto your CDB, happens in the 4th clock cycle. Now the second instruction load, though it was issued in the first clock cycle, because there is a dependence with the first instruction, it can't really start executing till the result becomes available. So it executes only in the 5th clock cycle, and it writes its result in the 6th clock cycle. It is only an integer add, so we assume that it takes 1 clock cycle. So it writes its result in the 6th clock cycle. If you look at the second clock cycle, again you issue 2 instructions. So your store instruction as well as the DAD-IU instruction are issued in the second clock cycle. The store instruction executes in the 3rd clock cycle, which is the effective address calculation. But memory access obviously can happen only when the operand becomes available, that is your incrementing instruction is over. So that finishes in the 6th clock cycle. So the store finally completes in the 7th clock cycle. So DAD-IU, though it was issued in the 2nd clock cycle, it executes in the 3rd clock cycle and writes CDB in the 4th clock cycle. So on and so forth, you can look at the various instructions. The only thing that I would like to point out here is, because this is a dynamically scheduled superscalar with no speculation, which means that you can, when you have a branch instruction, you can only fetch and issue instructions till the branch gets executed. You cannot execute instructions beyond the branch because you don't have support for speculation here. So as you can see, when you have a branch instruction, we normally look at a single issue for branch. So branch is issued separately in the 3rd clock cycle, branch gets executed in the 7th clock cycle, and the subsequent load instruction, though it is issued in the 4th clock cycle, it cannot execute till the branch has got executed. There is no support for speculation. So it executes only in the 8th clock cycle, 8th and 9th clock cycle, and writes CDB in the 10th. That is the only point that we will have to look at. So observe the fact that you are issuing multiple instructions every clock cycle. In this case, it is 2 instructions every clock cycle, and you are also checking for dependency by just encoding those dependencies into your reservation stations, and it works exactly like how we discussed for the Tomasulo's algorithm in the case of a single issue processor. And because there is no support for speculation here, instructions beyond the branch cannot be executed. You can only fetch them and issue them. Now when you look at support for speculation, you know that you can always extend the Tomasulo's approach with speculation, as we did in the case of a single issue processor. So in which case you will have to make use of a reorder buffer. So the reorder buffer is going to store the results from the time an instruction is executed to the time an instruction commits. So only when the turn for an instruction's commit arrives, you are going to transfer the data or the value that is available in the reorder buffer into your registers or your memory location. So we are looking at an in order issue, we are looking at an out of order execution and completion, and we are looking at a strictly in order commit. And because we are looking at out of order execution and finally an in order commit, you know that multiple instructions may be ready for committing. So, you may require multiple out of order execution and completion. First of all, the CDB itself, multiple instructions may finish execution at the same time. So, they might need multiple CDBs. So, you will have to have multiple CDBs if you are looking at a multiple issue processors. And when you are looking at transferring of data from the ROB to the register files and all that, you may again have to have multiple instructions. If you are trying to commit more than one instruction every clock cycle, you may have to look at increasing the number of write ports. So, this gives you an overview of the design of a speculative processor. This is the same as we discussed earlier. Only thing is, you know that you have a ROB also getting included. So, the operands instructions are taken from the instruction queue, they are dispatched to the reservation stations, a reorder buffer entry is also given, and instructions execute as soon as operands become available. The executed instructions will put out the data on the CDB. So, whatever comes on the CDB goes to the reorder buffers. So, that is what is the write that is happening. So, they do not write into the register file, but they write only into the reorder buffer, and instructions are strictly committed in order. So, every time a commit has to happen in order, you remove an instruction from the reorder buffer, commit it by writing it into either the register, or if it is a store instruction, write it into memory. And in case when you are committing an instruction, you find that your prediction was wrong. Suppose if you have a branch instruction and when you try to commit the branch instruction, you find that the prediction that you had made was wrong, then all your speculative execution is wrong. So, you will have to flush your reorder buffer and start fetching and executing your instructions from the correct path. So, this is an example with speculation. So, it is the same example here. So, it is a 2 issue processor. So, as you can see, 2 instructions are issued every clock cycle. They enter the decoding together, issue is done together. But if you look at the execution, that depends on whether there is a dependency between these instructions or not. For example, here load and then you have an add instruction which is dependent on load. If the add had not been dependent on the loaded instruction, then you can execute it along with the other instruction, provided you have a functional unit. But in this case, it is R2 value which is loaded and R2 has to be incremented. So, there is a dependency. So, the add instruction cannot execute unless the value becomes available. All that is the same as before. The only change is wherein you have a branch instruction. So, if you have look at the branch instruction, the branch instruction is still single issue. So, you issue the branch instruction in the 3rd clock cycle and the branch actually executes in the 7th clock cycle, and that is the condition checking happens in the 7th clock cycle, and the CDB write happens in the 8th clock cycle. Now, the subsequent instruction, load instruction, in the previous case we just fetched and issued the instruction, but we did not execute the instruction. But here the load is fetched in the 4th clock cycle, and you can see that the load is executed, that is the effective address calculation happens in the 5th clock cycle, and the load itself, the memory access itself happens in the 6th clock cycle, which is even before the execution of the branch. That is because we have support for speculation in the form of a reorder buffer. So, that is the main difference we have between a non-speculative execution and a speculative execution. Now, with this, with 2 instructions issued every clock cycle, we should actually expect a CPI value of only 0.5, because in an ideal setup with 1 instruction we got a CPI of 1. Now, with 2 instructions being issued every clock cycle, we obviously have to look at a CPI value of 0.5, but that is only an ideal situation. You find that there are many slots that go vacant, and depending upon the dependency among these instructions and all that, the ideal value may not be realized. Now, if you look at the implementation issues, there are a number of implementation issues that we will have to look at, and the design issues that we will have to look at. We know that we need to have each of the following steps to take place in one single clock cycle together. Say for example, you will have to fetch some number of instructions from the instruction cache and the branch prediction or the target buffer, because we are looking at issuing multiple instructions every clock cycle. So, you will have to apply the prediction, you will have to get the instructions, you will have to update the buffer on mispredictions and the cache misses. So, if there is a misprediction, all that has to be updated, all this will have to happen within one clock cycle. And speculation requires having a number of instructions in the instruction queue, because you are trying to execute instructions even beyond the branch, which means I need to stock up a number of instructions which can be executed. So, this requires having an integrated instruction fetch unit, which I have already pointed out when we looked at the Tomasolo's approach. So, because the instruction fetch unit becomes a very complicated unit, and the complication increases even more when you are looking at multiple issue processors, because basically you will have to fetch a number of instructions and issue a number of instructions in one clock cycle. So, the fetch unit becomes a complicated unit where you try to do a pipelining and you bring in different techniques where you try to look at fetching multiple instructions every clock cycle. And you may also have to look at non-blocking caches or caches that can respond with multiple refill lines per cycle. We look at what are non-blocking caches when we look at caches. Basically, the concept is, when you have a cache miss, are you going to stall the processor, or are you going to allow the processor to make further requests to the cache even though there is one block that has happened in the cache. So, we normally say, even if this has not hit in the cache, hopefully the next one will hit in the cache. So, we look at non-blocking caches. So, the details of this we will again look at when we are looking at the cache memories. So, now we will have to find instructions from the queue that can be issued in parallel, and also check the various factors that you will have to check are, when you are issuing multiple instructions, you will have to check whether there are reservation stations available for these number of instructions. Is there room in the ROB? Can you provide an ROB entry for these multiple instructions? How have you handled your war and war hazards through register renaming? Whether you have enough reservation stations and have you done the renaming process properly? And you will have to move instructions to the ROB, restrictions to the instructions that can be issued at the same time. Can I look at any type of instructions that can be issued together, or are you restricting on the types of instructions that can go together? All these are again design issues. One more limitation in terms of the time it takes to perform these tasks, that is a very important limitation, and the energy requirements. How much of energy do you consume when you look at performing all this within a clock cycle? Now, today an 8-issue superscalar is the largest that has been so far proposed, but in practice only up to 6 or 5 instructions, a 5-issue or 6-issue superscalar is possible, and you only have to look at in the order of about 2 to 4 instructions every clock cycle. Now, execution is not too much of a problem, because you can look at multiple execution units. So, you will have to execute at the functional units as data becomes available, and that obviously depends on the type of instruction that you are looking at. An instruction may finish fast, an instruction may have a longer latency, it may take a number of clock cycles to finish. And once they finish, you will have to send it on the CDB. So, because multiple instructions are executing, they may finish out of order, they may finish in the same clock cycle, you may have to have multiple CDBs if you do not want the CDB becoming a bottleneck. And committing the instructions in the ROB, again as I already pointed out, you may have to look at more number of read-write ports, otherwise your ROB becomes a potential bottleneck. Another design issue which we will have to look at is the window size. If the issue unit must look at n instructions, where n is our window size, to find those that can be issued simultaneously, it basically requires n minus 1 comparisons. So, if you look at a window of 4 instructions, it would require 9 comparisons, and if you look at 6 instructions, that would require 25 comparisons. So, as you keep increasing the window size, the number of comparisons that you have to do keeps increasing, and that becomes a limitation to the increase in window size. So, these comparisons must take place in a short amount of time within that clock cycle, so that the instructions can be issued at the same cycle and the data forwarded to the reservation stations and the ROB. So, there is a lot of work to be done in one cycle. So, the modern processors have a window size of only about 2 to 8 instructions, although the most aggressive has a window size of 32. And remember that the window size depends on only how many instructions can be compared and not on the number issued. The other important factor is what happens when you have a misspeculation. So, what is the cost of misspeculation? So, if you calculate the cost for misspeculation and if you find out that it is too large, is it worthwhile doing a speculative execution, or should you have to really wait for the branch to be resolved and then go in for a non-speculative execution? That is another question that arises. But normally we find that predictions are very effective, speculative execution is very effective. So, we normally go in for speculative execution. And particularly with floating point benchmarks, even though the result is not too good, the result is very good because your misspeculated code is only about 5%. With integer benchmarks, the misspeculation is a little high. Now, similarly, another issue that you will have to look at is speculating through branches. Suppose if you are already doing speculation with respect to one branch, do you have to stop there, or do you have to look at speculating across different branches? That is another design issue. And how much to speculate? How much are you allowed to speculate? Because say for example, you are trying to do a speculation and you are doing a speculative load. Suppose when you are doing a speculative load and the load misses in the cache. So, are you going to just look at the load missing in the first level cache or the load missing in the second level cache? So, how much of speculation are you actually going to do? Because there is a risk that is involved, but how much of a risk are you actually willing to take? Because speculative execution itself is taking a risk. So, how much of risk are you actually willing to take? So, normally processors decide, okay, till this level I am willing to speculate. Otherwise, if you find that it misses there, then I will not do further speculation. I will wait for the branch to be speculated. So, these are some of the main issues that we will have to look at when you look at speculative execution. So, looking at the characteristics of multiple issue processors, this slide gives you an overview of the different types of multiple issue processors that we have looked at. Your statically scheduled superscalars, dynamically scheduled superscalars, and the VLIW processors. An additional category that is given is the EPIC processors. The VLIW and at least an introduction to EPIC will be done in the next module. So, to summarize, we have looked at the need for multiple issue processors, because only if you look at multiple issue processors, you are trying to exploit further the instruction level parallelism available among the processors, and we are trying to reduce your CPI value less than 1. So, multiple issue processors can either be superscalar processors or VLIWs. Superscalar processors can be statically scheduled, where you look at in order execution, or they can be dynamically scheduled with and without support for speculation, where they are allowed to do out of order execution. The compiler is complicated in the case of statically scheduled processors, whereas the hardware becomes more complex in the case of dynamically scheduled processors. Dynamic scheduling can obviously be combined with speculation also, with support for ROB and all that. And there are several design issues like the issue width of the processor, how much do you speculate, the window size, and whether you allow speculating across multiple branches and all that. All these are design issues which will have to be decided at when you design the process. So, thank you.